Good morning, everybody. Today we will talk about the energy level and the line spectra of atoms. We also will discuss the line absorption spectra of different atoms. Here's an example of an element that has different energy levels, wherein photons go to a higher level, and when they fall down, they will release a photon with a certain frequency, and that's why we get the line spectra of an atom. We will elaborate later on how this is different for different atoms and why is that. So, we explain the occurrence of a line spectra of, for example, atomic hydrogen as an evidence of transition of energy levels in atoms, and this transition of energy level is discrete. We will also discuss the energy that is emitted by the photons using the equations HF E1 minus E2, and a little bit about the terms ionization and excitation. Okay. When we have a gas discharge lamp, it produces light. When the gas discharge lamp is switched on, the gas is ionized. Free electrons accelerated by the electric field in the tube collide with the gas and the metal atoms. Yeah? Some electrons, they are like circling around the gas, and metal atoms. They are excited by these collisions, bringing them to a higher energy state. So electrons in an atom have a certain ground state depending on the atom. The people who have studied chemistry, they know a little bit more about it when we are talking about the electron configuration of an atom. And they know that electrons occupy certain energy levels at their ground state. Now, when the electron gets this energy, it will directly fall back to its original state. It emits a photon, resulting in visible light or ultraviolet radiation. So, energy is going in. The electron is at a ground state, then it will, because of the energy input, go to a higher state, and then it will fall back to a lower state. Now, when it falls back to a lower state, there will be a photon emission, and it will release light with a certain frequency. So, an energy input raises the electron to a higher energy level. This energy input can be either electrical, heat, radiation, or particle collision. So, for example, when you have a bulb, and a bulb is nothing more than a wire in a glass tube, to say so, electricity current goes in, the wire is going to heat it up, and it will excite the electrons, and at the same moment, the electrons that are excited, they go to a higher level and they will fall back. When they fall back, they release photons, and that's why a bulb releases light. Yeah. So when the electrons fall back at a lower level, there's an energy input. This occurs by the emission of a quantum, or we say package of radiation. So whenever possible, electrons always try to occupy the lowest energy level, and we call that the ground state. I will show you now a clear instruction video about how electrons are excited in an atom and how they can fall back in different energy levels.
In the last video, we looked at how electrons can only exist at certain discrete energy levels within the atom. They can't really exist at anything beneath that, they just fall down to the shell below that. And what we have here is the spectral transitions for atomic hydrogen. And we can go from the ground state, where n equals 1, right up to the electrons basically escaping that atom and making it an ion. And as we look at all the things that could maybe drop down to the ground state, we can have things that move from this n equals 2 down to the ground state, or perhaps n equals 3 or 4 or 5. We can also look at the various energy changes that we might have down to the n equals 2, and also the various energy changes for n equals 3. And because every time we have an energy change, we have an associated frequency, or therefore wavelength, of light emitted. And effectively, what we have is when the electrons move down by a huge amount, we get ultraviolet light given off. So there's some ultraviolet photons being given off at this part of the spectrum. In the middle part, they aren't as energetic. The energy changes aren't as big, so the frequency isn't as big, and therefore we maybe have visible light given off at this part of the spectrum. And finally, these are fairly small energy changes over here, so we might have infrared light or infrared photons which are given off. And effectively, you can only have certain values of photons given off, and therefore certain values of wavelengths of light which are emitted by hydrogen. What we can actually do is look at the various colours of these emitted photons. And what I have here isn't actually hydrogen, this is helium. And what we can look at are the various wavelengths of light which are emitted. And effectively we have the visible spectrum here going from the violet end right through to the red. And what we call this is an emission spectrum. So this emission spectra shows a certain wavelengths of photons which are given off by helium. As it's excited, we might have a load of helium gas which is really hot, full of lots of energy, and as the electrons drop back down to the various sort of ground states and the lower energy levels, they emit certain wavelengths of light. And for every single element, it has its own particular emission spectra. How do we see this? Well, we see all the kind of colours sort of mixed together. So we might see the yellow adding to the red, to the green, to the blue and the violet, and what we might see is white light. So how do we actually get the spectra? Well, what we have to do is we need to shine that white light through a diffraction grating. And what this does is it splits up that rainbow of colour and really shows us the certain frequencies of light that make it up. However, this emission spectra also has its kind of twin brother, and this isn't so much things being emitted, but this is things being absorbed. Now, we've already seen on the model that when an electron drops down, it emits a certain photon of a certain frequency. Well, in actual fact, when this goes up to the next level, it only emits or only absorbs certain frequencies of radiation. So this one here maybe might emit a photon with a blue wavelength which goes out, but in order for it to get up to the next level, it has to emit a blue photon. A red photon, a green photon, these don't have quite the right energy. It's very, very picky about who it chooses. So this photon comes in, it excites the electron and it moves up an energy level. And therefore what we have is not just an emission spectra, but we also can see an absorption spectra. An emission spectra is given out by something, but an absorption spectra is when you maybe have a cool gas and you shine a load of white light through it. So white light being made up of all of the colours of the rainbow. And what we find is that only certain colours or only certain photons are actually absorbed by whatever we've got. And what we see is like kind of, I guess, like an anti-emission spectrum. And we see a black line where no light kind of gets through. So we find that actually certain frequencies of green light are absorbed, and therefore there's like basically a bit of a gap in the spectra. And this is really, really important, okay? This gives us evidence for the fact that what's inside stars, that there is actually helium inside stars. It gives us evidence for the fact that the galaxy and the universe, in fact, so not the galaxy, but the whole universe is expanding. And it's because what we can do is by looking at starlight, we can start to see the various chemical elements that make up the kind of the outer atmosphere of those stars. So an absorption spectra is where certain frequencies of light are missing because they're being absorbed by that element. So we know that helium absorbs certain yellow, red and green and sort of different frequencies like that, whereas when it emits stuff, it only emits the same things. And this is because the frequencies which are absorbed by the electrons to move up the levels are the same as the photons given out when these things drop back down to their ground state. So that's what quantum physics really leads on to, basically work on stars and rainbows, and how by knowing about what's inside the atom on the very, very smallest scale, we can then start to investigate things on the very largest scale in our universe.
So let's talk about the quantization. So in a quantum mechanical system or particle that is bound, it can only take certain discrete values of energy. This is opposed to the theory of classical particles that can have actually all energies. These values, we call them energy level within the atom. So it's mainly used for atoms or molecules which are bound by the electric field of the nucleus. Okay. So the energy spectrum of a system with energy level is said to be quantized. Packages of energy. Okay. Now let's look at these models. If we look at the complete spectrum of white light, that is the visible spectrum. Now, then we look at hydrogen. Hydrogen has only one electron, but it can have different types of energy levels. So, when hydrogen gets excited, it can go to a higher level, only packages, and it can fall back, and it can fall back in different states, and that's why we see actually like ultraviolet line, blue, light blue, and red. Now when we move up in the periodic table, and especially the chemistry students, they know that when we talk about the electron configurations, more electrons occupy different energy levels. Therefore, these electrons can be excited from the ground level to a higher level and jump back. So there are lots more of possibilities. When we move up even to iron, we see even more and more lines. Okay, but remember, when we look at the electron configurations of the elements, and they have like energy levels or in orbitals, okay, they can get excited and then fall back. Okay, so when there are more electrons around the nucleus, there are more possibilities, but there will never be a continuous visual spectrum. Okay, so each element has its own specific set of lines, and this is what we call the line emission spectra. Now, what do we mean by line absorption spectrum? As was mentioned already in the video, when light of all frequencies is passed through a gas, then the gas only absorbs the light of the same frequencies as it would emit. So when we look, for example, at the hydrogen, we only would find those 4 black lines. That means that one red, one light blue, one dark blue, and violet is being absorbed, and the rest is passing through. Okay. When we move up in the periodic table, depending on the atom, you see that we will see more and more black lines. Okay. Now, as we know, we can actually, when we look at an element and we pass light through it, we can actually see which energy levels have been absorbed, and by which is related to the electron emission spectrum, which we can relate to their wavelength or frequency. Okay, so each element has its own unique line emission spectrum and line absorption. So here we can look at the energy levels of hydrogen. We have like a ground state, and the electrons, they can get excited to different levels and give off different types of light. Okay, so an electron can get it excited, can go up to this level, and then fall back down to a lower level and emit light. Or when we look for the red light, we see it goes to this level and then falls back to this one, and it will give off a photon of red light, etc., etc., etc. Okay. Okay, let's talk about again the energy level and the energy that is related with it. Yeah. So first of all, it's interesting to know, why do the states have negative energy? Why not positive? This is simply because the zero of energy is considered to be that of a free electron just outside the atom. So that is the zero level, okay? So that is like an electron has given so much energy that it just can escape, okay? All energies below this within the atoms are therefore negative, yeah? The energy must put inside the atom to raise the electron to the surface of the atom and allow it escape. Yeah, then it will reach the energy level of zero. So you have to put energy inside the atom. And this can be done by heat, electricity, radiation, etc. Okay, the equation for the energy of the photon that is being released, we have the energy in HF is E1 minus E2, yeah? The energy of the emitted photon is the difference between the energy level, okay? And we used this equation before, okay? And we know when the frequency is much higher, the energy of the photon is much higher. So that's the reason if, and we go back, that's the reason if a photon is excited at a higher energy level and falls back over a greater level, so that means that the energy level of the excited state minus the ground state is high, we will see that we will get a photon with a higher frequency. Is that difference in level lower, we will see light of lower frequency, so more in the red region. Yeah, this energy is stated in, there it is again, the electron volt. Yeah, and we know that is 1.60 times 10 to the negative 19 joules. Yeah, remember, the electron volt is the kinetic energy gained by an electron when it is accelerated through a potential difference of 1 volt. Okay? That's it for now, and I hope to see you next week, and then we can continue more with quantum physics.